Yes, Ibrahim, Jobita, is it audible? Jasleen?
Yes, ma'am. Yes, ma'am.
Okay, good evening, class. So we just started with magnetic field. We didn't complete much of it. Let us just continue. See, we studied about the basics about magnetic field, that around every magnet, whether it's your bar magnet, horseshoe magnet, any sort of magnet, we have a space where only magnetic properties can be experienced. Beyond this, it cannot be experienced. That is known as the magnetic field, and there are various properties of these magnetic field lines that we'll study later on. Right now, we discussed that SI unit is Tesla, represented with capital T, and CGS unit is Gauss, represented with capital G. And we discussed that one Tesla is equal to 10 to the power 4 Gauss. Now let's talk a little bit about the sources of magnetic field, which we didn't discuss earlier. Look, regarding the sources of magnetic field, if you have, just a second, let me reshare the screen. Yeah, so let's talk about the sources of magnetic field. In class 11th, you must have studied about the atomic structure. There, you must have taken out the values of L, values of S, like this. Remember, there was a spin, intrinsic electronic spin. M was there. Values are taken out from the shell, like 4s is given, 3p is given, like this. How do you calculate? So there you had a value of intrinsic spin of electron. Intrinsic spin of electron. When we talk about the intrinsic spin, you must be remembering it was represented by a plus half or a minus half. This is how we represent the intrinsic spin of electron. That also creates the magnetic field at a very micro level. Let's move further. Then we have a wire. Let's say this is a wire which is carrying current. This also at a particular point, let's say at this point or any point, also conducts the magnetic field. So this will be current carrying wire. This will be a current carrying conductor. I'll write the conductor. Now, apart from it, you have the actual magnets present. There are magnets in this shape known as the bar magnets. Some magnets are in this shape. These are the two common magnets which you will find it in your labs also. Like this. This is the horseshoe magnet. So actual magnets produce magnetic field. Then you have the iron ores present. Fe2O3, FeO, all these different variable states of Fe, iron. Also, you have devices like solenoid that we'll be studying in this chapter once we discuss Ampere circuit law. Solenoid is there, then other devices are there. This is called a toroid. Basically, turnings of the copper wires are made which carries current. So there are various sources of magnetic field that we have. In short, all these magnetic field are present. And see, this was there in your chemistry. This we'll study about bar magnets and all. You will study it in the next chapter, chapter 5. The iron ores are again a part of your chemistry. Solenoid and toroid, we will be doing it in this chapter. Okay, so write down this class. I'll start with Biot-Savart's law, means this portion, current carrying conductor. Okay, please write it all. Done. Completed? Have all of you written? Okay, then I'll move forward. Coming to the Biot-Savart law class. See, what does this law say? I hope I'm audible to everyone.
Yes, ma'am.
Okay. This is a very important law and a very basic law for your magnetics. Like you had Coulomb's law there. This is your Biot-Savart law. We have a wire. Okay. This is a current carrying element. We say current carrying conductor. A wire is there which is carrying some amount of current, let's say I. Okay. Here at a point, let's say P, I want to find out the magnetic field. It's like the wire is here and I want to find out the magnetic field at this point. So this is the current carrying wire and this is the point P. And the separation from the wire to the point P is R. Now, for the convenience, we are going to consider a very small current element. In the sense, if I take a very small length of the wire, which is the current element. Okay, a very small length of the wire I have taken. So this is DL. We are going to consider DL because we are going to talk about different kinds of shapes. So if we know DL, we can find out the rest of the shapes also. For different shapes, we can find out the values of magnetic field. So I have taken here DL, that is the current element. This is called as the current element whose direction is same as that of the current. But it's nothing, it's just a small length of the wire that is taken. Okay? And see, between the current element and the position vector, the angle that is formed is taken as theta. So what all things do we have? I is the current flowing through the wire. DL is the current element. R is the position vector and theta is the angle between DL and R. Okay. The variables are clear to everyone. Can we move forward? Yeah.
Yes, ma'am.
Okay. Let's go next. See, now according to this law, Biot-Savart's law, this says that magnetic field is proportional to three things. First, it is proportional to the current that is flowing. Okay. It is proportional to the current. Second, it says the magnetic field we have taken a very small value. So this magnetic field is proportional to the current element as well. Current element is nothing but just a small length of the wire taken so that we can perform our integration and solve it in a better manner. So this is current element. Okay. Now we have taken this angle. This is theta between the wire and the position vector. So here we are going to say this is directly proportional to sine theta. Now the fourth point, it is inversely proportional to the square of the position vector again. So this is under your inverse square rule category. This is following inverse square rule. Whenever you have class r square in the denominator, that comes under inverse square rule. So these are all the things. This is how your Biot-Savart law is divided. Now, when I combine all of this, I'll have dB is directly proportional to I into dl into sine theta divided by r square because it is coming in the denominator. It is inversely proportional. All right. Now here again there a constant will come to remove the proportionality sign. I dl sine theta divided by r square. Now compare it with your electrostatics. The constant in electrostatics that we have studied was 1 over 4 pi epsilon naught, whose value was 9 into 10 to the power 9. Now the constant that we get, in fact, I'm removing this dB also because we can just write a proper formula. Magnetic field is mu naught divided by 4 pi into I dl sine theta divided by r square. This is the actual law, final formula of Biot-Savart law. All right. Now coming to the constant, what are these constants? What is this mu naught? What is this 4 pi? I'll talk in detail about it. You write it everything till here about this law first, understand it. If there is any problem with any variable, you are not understanding the meaning of any variable or anything, please just let me know. I'll make you revise that. Then I'll tell you the detailings about the constants. Right now, I'm just stopping at the point that mu naught by 4 pi is the constant. Write it till here, comprehend, then we'll go further. Okay, please write class. Done?
Yes, ma'am.
Okay. C class. Now let's talk about the permeability. This mu naught is the permeability. Like we had permittivity, epsilon naught, here we have permeability. See, there's a difference. Permeability and permittivity, the basic difference is about the fields. You know, that was referring to your electric field, electric forces. This is completely referring to magnetic field only. Epsilon naught governed the forces. This governs the magnetic field. That's it. This also, mu naught tells you how your medium is going to change the values of magnetic field. So the epsilon naught is basically permeability, allows the magnetic field to change with the medium. Okay, allows the magnetic field to change with the medium. So different values, you will have different values of magnetic field. Different media you're putting the values of epsilon. Now, one fixed value is mu naught's actual value is 4 pi multiplied to 10 to the power minus 7. So here this complete mu naught by 4 pi can be written as 10 to the power minus 7. Okay, this is what the absolute permeability of free space is. But when we put a naught, basically the real symbol for permeability is this mu. But when you have the permeability specifically for air, means air is your medium, then it becomes mu naught. That is the absolute permeability of free space. But mu you have for any medium. So when you are comparing it, the relative permeability you are taking, okay? Mu is the permeability of any medium. Mu naught is for free space, air or vacuum, okay? So if you have any other medium present, see, mu divided by mu naught is equal to mu r. If you remember, we did the same thing in case of epsilon naught also. Epsilon by epsilon naught is epsilon r. You're comparing something with respect to air. You're comparing the value of mu in a medium to the value of mu in air. That is giving you a relative value. It is giving you a ratio. So here you use this, you will get your answer. This one is your relative permeability of a medium. Just a slight difference is about the material and the medium. That this is allowing the magnetic field to change, not the magnetic force. While your epsilon naught permittivity was allowing the forces also to change apart from your electric field and rest of the things. So this is the difference here. Now you can always use mu is equal to mu r into mu naught. Let's say we have the value, I'll just use this as b. So b is equal to mu, some medium is there, mu, by 4 pi I d l sine theta divided by r square. So when you put the value of mu as mu r into mu naught, this will be mu naught into mu r I d l sine theta divided by r square and 4 pi here. This is the value which you can use and mu r will be mentioned to you. Okay, mu r will be given like in your weekly test which we discussed. There the value of epsilon r was given, which has come in your board exams. So you will directly get the value. You don't need to remember any of these values. Okay, values will directly be provided. But you should know the value of mu naught by 4 pi, which is 10 to the power minus 7. Okay, mu r is the relative permeability. In the next chapter, we'll see various kinds of substances like diamagnetic substances are there, ferromagnetic, paramagnetic, and all different types of substances are there. So for them, the relative permeability plays a crucial role, and you have to remember the values. Values as in certain ranges so that you can compare the different materials. Okay, not exactly one particular value. So like ferromagnetic substances have the relative permeability greater than 100. For iron, it is almost 1000, which is a ferromagnetic material. It's an example of it. Then diamagnetic materials have lesser than 1, 0.0, something like this. So this is how you have to use the relative permeability in the next chapter. That's why I've just mentioned a bit of it. In detail, we'll do it in that chapter. Coming to the vector form of the magnetic field. How to write the Biot-Savart law? See, you have mu naught by 4 pi, no change in here. I, now you have I dl sine theta, right? You will use here R cross dl. Oh, sorry, dl cross R. Here you are going to put dl cross R. Okay, divided by R cube. Look, class, when you open this is a cross product. It will automatically become what? Look, this will become dl R sine theta divided by R cube. This R and R cube will be cancelled. So again, dl sine theta divided by R square only will be left. So it's the same thing over here. Okay, but in vector form, you should write it like this properly. Mu naught by 4 pi I dl cross R divided by R cube. This is your basic of Biot-Savart law. We'll see the direction part and then we'll come to the NCERT questions. Tell me, class, have you understood this? Everyone?
Yes, ma'am.
Others, Jobita, Jesleen, Shaima, got it?
Yes, ma'am.
Oh, write it. Then let's have a discussion after it. Direction part I'll do. And please, class, for the direction part, everybody open the camera. Okay, because you will be following along. We'll be using the hand rules. So right now I'm telling you, after this, please have the facility to open your videos. Yes, done. Okay, class, please switch on the videos and let's understand how to write the direction. See, there are various kinds of rules that you have. Left hand rule, right hand rule, this rule, the Fleming's rule, you must have studied already, that was there in your syllabus. Now see how you have to follow the rule in case of your magnetics. Remember, here throughout your magnetics, we are just going to use a right hand. So that you don't get confused, with just the right hand, we are going to learn all the kinds of rules that are there. So don't get yourself confused with the left hand. Okay, always take your right hand. Now there are two methods for this one, for a straight wire, for a straight line. One first method I'm telling, which usually I prefer less, but many students find it convenient too. So you can go for that. You have to point your thumb along the direction of current. Let's say this is current. Okay, current is going upwards. So then we'll have our, take your right hand, we'll have our thumb upwards, right? Right thumb will go upwards because the current is going up. Now see, where is your point? Point is, let's say this is the point A. Okay, this is point A. So where at this point A, where are your fingers going? Look, these are the fingers. At this point A, the fingers are pointing towards me, right? This is point A. This is upwards direction. So when I am curling the fingers at this point A, the fingers are going towards me. Towards me means out of the page. Okay, this means this is out of the page. So here the direction of current will be outwards. B point I'm telling you. Any confusion in this class, please stop and do it along so that you are able to understand. Okay. Current going upwards. So right hand, thumb upwards. This is fixed. But this time, the point isn't here. Earlier the point was here. Now the point is here. So we are going to curl our finger at this point. Look, for this point, the fingers are going inside. So at this B point, the direction is inwards. Tell me, have you all understood this? Yes, no, kya?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Got it? These are the written part only. This is the written part. Hold the wire in the direction such that the thumb points in the direction of current. Okay. The curvature of finger, wherever the point is there. Like I had the point here, so I curled it like this. If my point is here, I'll curl it like this. So curvature of finger points along the magnetic field. This is the rule. Okay. So all of you try and tell me the answers. Right now, I don't think so. It will take much time. Okay, this we have discussed. You tell me for this one. Second one's A point. Just type it in the chat box. Where is your finger leading? Inwards, outwards, up, down. It can be any direction. Yes, just now you must have got the answers. Yes, very good, Ibrahim. Correct. Apart from Ibrahim, see how thumb is pointing downwards. Okay, Shaima. Okay, Justine. See, thumb is pointing downwards. Justine, your answer is right. Okay. Look at this A point. Yes. Now it's right, Shaima. Correct. See, inwards. Thumb is pointing downwards. Point A is here. So when you're curling the fingers like this, when you curl it, at this point the fingers are going inside. So this is inwards. Class, can you tell me for this B point? Same thing for this B point. What's the direction coming? Yes, Ibrahim, correct. Shaima, correct. Yasin, correct. Very good. See, thumb is still downwards. Thumb is pointing downwards. Correct, Jobita. Very good. All of you have understood this. At this point, see, this is the point. So when you're curling it, the fingers are going up. So that's the rule. I'm again saying don't use your left hand. If I use the same thing with the left hand, look class, downwards, the B point is here. When I curl it, this is coming inwards, right? And with this, it is coming outwards. So your answers will be exactly opposite. Don't bring the left hand in any case of magnetic field. I'll not give you a single rule. I'll just tell you all the rules with the right hand so that you're not confusing with the left ones, because there are many rules for magnetism. Okay. So first, in every rule, we are going to use right hand. So be careful in the exam also, use your right hand so that you are not committing the mistake, because for every hand, the rules are different. Now, second method I'll tell you, this is a simpler method. In the previous one, it was a little difficult to identify, okay, where are the fingers exactly pointing, going inwards, outwards like this. This is relatively easier. I'll show you in this one first. Current is going upwards. Now, class, do it here with me only so that you are able to understand. And if you have any doubts, you can ask. This time, don't take your just thumb. Don't just take the thumb. Put the palm along the direction of the current. Okay. So this way means your tips of the fingers should point towards the direction. So current is upwards. Now I have put my palm upwards. Okay, in the up direction. Now you have to curl the fingers along the point. Where is the point? So see, if I put it like this, point is here, I'll not be able to curl. If I put it like this, point is here, now I'll be able to curl. See, where is the thumb pointing? Outwards. Same answer, I'm getting outwards again. So this one is the one which I prefer, because easily the answer comes out. The curvature one, I find it a little difficult and confusing sometimes in the clubbed questions. Come to B point. Look, now this is current is upwards, so we are also putting upwards. Now I have to curl my fingers towards the point. So if I keep my hand like this cannot be curled. If I keep it now like this, but B point is here, this way it cannot be curled. This way also it cannot be curled. So if I keep my hand like this, point is here, curling. Thumb is inward. So straight away the answer is here. No, not anti-clockwise or clockwise. Okay, because for anti-clockwise and clockwise, that is a circular part. For that, I'll tell you. Circular one has a different method. This is just for straight wire. This will be inverse. Yeah. So the second method is clear to all of you. I'm repeating it. Means the lines. Place your fingers along the direction of current. Okay, and curl it towards the position vector, means the point where you are calculating. Point is here, curl it like this. Point is here, curl it like this. Wherever the point is placed, then the thumb will give you the direction directly. It will point outwards, inwards. You don't have to predict anything. Is that clear, all of you? Jobita, Ibrahim, Shaima?
Yes, ma'am. Yes.
Yes.
Okay. If it is clear, then in the chat box, tell me for this A point. Use with this method, okay? Apply this method. After this, whichever method you are convenient with, you can use. Both the methods are valid. Yes, very good. Correct. Oh, Ibrahim has answered both of them. Just in right. See, class, this time, Jobita and Shaima, see, now the current is towards the right. So we are going to put our hand pointing towards the right. Yes. Correct. Very good, Shaima. Right. This is correct. Hand towards the right. Now point is above. So this position is correct. If I curl it towards the point, thumb is pointing outwards. Look for the second one. Now, the current has this direction. Point is downwards. If I still put it like this, I'll not be able to curl it. At least I'll not be able to curl it. And I hope you all also will not be able to curl it. So keep your hand in this direction where you are able to curl. Okay? Because there is only one direction possible. So that's why you will definitely get the answer. So thumb is pointing inwards. Tell me for this one, A and B both. This was outwards. Yes, right, Ibrahim. Jasleen for this one. Jasleen, recheck. Yes, Shaima, correct. For this second example, A and B point. And yes, Ibrahim is right. Jasleen, so Jobita, your answer? You getting Jobita?
No, ma'am. Getting confused.
You are confused. Jobita, switch on the camera. I'll help you. Let's do this example, okay? For A point, we are solving. Now, Jobita, take your right hand. We are going to place our right hand in such a direction where the current is moving. Look, where is the current going? It is going towards the left, like this. This is the arrow, how it is pointing. So we are also, it means our hand will be towards the left. Okay. It can be like this, like this, like this, like this, whatever. Okay, but it is towards it. Now see, where is the point A? If this is the current, isn't the point A above? Look in the figure. Here, this is above, right? If I put my hand like this, I have to curl the fingers at this point. Will you be able to curl it like this? No? So if we place our hand like this, now are you able to curl it for a point above? Yes. Where is the thumb pointing? Means towards the screen or towards you?
Towards me.
Towards you. You've taken your right hand? Yes. Is that you?
No.
Then after doing the correct answer, that now Jobita, this confusion cannot be solved. Is this the screen is you or whatever is it? Okay. So this is how you have to write that. Now is it clear? Now Jobita, try for B point. You tell me for B point. And Jasleen, what about your answer? Was it revised? Could you do? Jasleen, now you've got the incorrect part. Yeah, Jobita, tell me for this B point. This we did. It was outwards. This was going inwards. Yes. What are you getting for this one? Yes.
Outwards. Out.
Out. Yes. See, hand is placed like this. Point is below this time. So now we'll be able to curl our fingers. See, the advantage is that your hand has only 1 degree of flexion. Means in one plane only it can be curled. So you'll always get a definite answer. Except if you can do circumduction, that's different. But you will normally, in normal cases, you'll get a single direction. So this is outwards, okay? Right. Now, whichever method you all find convenient, you can use. I prefer this one. So in most of the questions, I'll get my answer like this. But if you are getting confused, you can use the first one also, okay? All right. Write it. Then let's, yeah, this is an NCERT question. We'll practice this. Please write this first. Ibrahim, right now you have the class at Learnivio.
Yes, ma'am. Yes, ma'am. Now only we have. I have.
9:30.
No, yes, ma'am.
Just wait. Just give me a minute, Ibrahim.
Yes, ma'am. Yes, ma'am.
Yes, Ibrahim. Please go and join the math class. This half an hour recording you can watch. Or if you have any doubts, we'll contact. Okay? You go
Okay.
and join the
Okay,
class.
ma'am. मैं खड़ी Okay, chalo. Thank you.
Zobita, you saying something? Zobita, are you asking something? No? Okay, class, quick revision of your cross product, just about the directions. How you solve dot product, we've already done, and that won't be needed here. But now you can be asked to write about the universal unit vectors because of the direction. See, if something is pointing towards the positive x-axis, so rather than saying towards the right, towards the positive x-axis, you can write I cap also. With this, many questions get solved also. So that's why I have just written this so that it can be used as a revision. We did this in 11th also, and I told you that just write I cap, J cap, and K cap. You move clockwise, that will be positive. You move anti-clockwise, it will be negative. Now what? If it is I cross J, means I cap cross J cap, then which one is left? K cap? We have moved clockwise, so it is a positive. Similarly, J cap cross K cap, we are what is left? This is I cap, so this will be positive because we are moving clockwise. Now K cap cross I cap is J cap. Now if we are going reverse, means J cap cross I cap. So see, J cap cross I cap, we are going anti-clockwise. So which one is left? K cap, negative. I cap cross J cap, minus J cap. K cap cross J cap, minus I cap. So please be aware about the direction. This question, let's discuss a very easy question. It's from your solved examples of NCERT. Look, this says that you have to calculate the magnetic field at this P point. Here is your P point. For those who are relocating it, this is the P point. Okay. Now see, this is separated from the origin by 10 meters. And the small length that is given, 0.001 meter. That's your current element. Always remember, current element is just a small length extracted from a wire. If I have a wire and I just take a very, very small portion from here, that is like your current element, where the current was actually flowing. And current is given as 10 amperes. So B is equal to mu naught I dl sine theta divided by 4 pi r square. Now mu naught by 4 pi, what did we discuss? What is mu naught into 4 pi or mu naught divided by 4 pi? Not mu naught into 4 pi. What is the value of mu naught divided by 4 pi? Anyone? We discussed it. 10 to the power minus 7. Yes, very good. This is 10 to the power minus 7. Correct, Jasleen and Simon. 10 to the power minus 7. So this is 10 to the power minus 7. Multiply 2. Current is given as 10 amperes, so 10. DL means a very small length. So small length is this. 0.001. Can I write it as 10 to the power minus 3? Same thing. And then sine theta. Sine theta, a very great value we have, that is sine 90. Straight away one. Calculations are easier. And radius means where your point and the current element is separated. See, the thing with this question is to identify what all variables are there. Because once you look, it becomes difficult to analyze that is this the wire? No, as this is your wire. Here the current is flowing along the x-axis. Point is taken perpendicular to it on the y-axis. Okay. Rest the solving part is very easy. You'll be able to do r square means 10 square. So 10, 110 will get cancelled. 10 to the power minus 7 minus 10. So 10 to the power minus 9. This is minus 10, yeah. But this goes above, so minus 10 only. This will be 10 to the power minus 10. Now class direction. Try the direction, whichever method you feel like. Tell me in the chat box the direction. Because it's given in the coordinate form means your axis, answer in terms of axis. That is your I cap, J cap, K cap.
I cap.
I cap. Any other answer? Jesslyn says J cap. Okay. Look, where is the current flowing? No, not J cap. Why are you people getting J cap at the end? See. Current is flowing towards the right. So hand towards the right. Point P is perpendicular. Curl it. Thumb is coming outwards. The third axis, Z axis. Didn't we do this? See, we have done this question before. Current flowing like this, point A here. Same thing. It was outwards for you all. So right now it's the same thing. Current is going along x-axis, class. So we have to keep our palm along x-axis. Point is above. P is perpendicular, so curl it. Thumb is outwards. Outwards means positive K cap. So this much K cap lies the answer. Now got it, all of you? And got it? Okay. Shaima, you too?
Yes, ma'am.
Quickly write this cross product thing, class. This and okay. One or two things, then we'll complete this. Just write the cross product very quickly. This you must be already remembering. Okay, class done. Shaima and Jobita, you both have written?
Yes.
Yes, ma'am.
All right. See, there is one small question that has come. Directly formula-based questions have not come till yet from this portion, means the one which we are doing, this note part. But it's very easy, and that can come because it's there in your NCRT. Current is dq over dt. Now, the formula of magnetic field is mu naught I dl sine theta divided by 4 pi r square. Now, class, if I write down this formula here, I substitute it here. B is equal to mu naught by 4 pi. Instead of current, I am putting dq over dt into what's left? dl into sine theta divided by r square. Can any one of you by any chance tell me this? What is this? dl over dt.
Speed.
Yes, very good. It's velocity, correct. Not speed, because here we are talking about vectors, but velocity. Very good. So velocity is dl over dt. Okay, this is L. So the formula that you have is a quite different formula from your Biot-Savart law. It's a modification of it. Mu naught by 4 pi dq cross this velocity v divided by r square, which you can write as v is equal to mu naught by 4 pi dq v sine theta divided by r square. This is also a rule. When you will just get current, the charge, suppose a question is given, the charge is flowing with a certain velocity v. Calculate the magnetic field at a point of 10 meters away from the charge, like this, if it gives you. So you don't have any information about current element is not there, just the position vector is there. So using the charge, velocity, and r, you'll be able to get it because mu naught by 4 pi you already know. So this is also an important formula, this one. In vector form, this you'll be able to write it by yourself. Okay, now see, coming to the applications of Biot-Savart law. In Biot-Savart's law, there are two things that can come. One is about a straight wire, one is about the circular wire. In straight wire, you have three categories. One is an infinitely long wire. Infinitely long wire. Second is finitely long. Infinitely means both the ends of the wire are extending up to infinity. This is also going to infinity. This is also going to infinity. Second is a finite wire. Like from infinite wire, I've just cut this and I've taken this wire. So this is finitely long wire. Then you have one more category with you, which is semi-infinite wire. Now, class, the derivation of any of these is not there in your syllabus, so don't do it. But in your board exams, this is included, this is deleted, this is included. So just remember the formula, this whole part is solved. I'll tell you the formula though. And coming to the magnetic field due to circular coil. Here also we have three things. First is the circular loop. Circular loop means a complete proper circle. Second is a semicircle. Third is any arc. Any arc, okay? Any circular arc means it is subtending any kind of angle. Any circular arc. All the derivations are there and all the formula are there. And the final questions that come is in combination of all of these. Means infinitely wire bhi hoga, फिर semicircle wire hoga, then a circular loop would be there like this. So remember the formulas individually. I'll show you the kind of questions that are there. So this is how it is distributed. Let me tell you the formula of infinite and semi-infinite, and you can copy, and I'll end the class because, yeah, questions we'll do it in the next class. See, for infinitely long wire, when the wires ends are extending up to infinity, this is pointing to infinity, this is pointing to infinity. So at a point P, we have taken a separation that is A, making an angle of 90 degree. Current goes up. So magnetic field has a formula mu naught I divided by 2 pi A. This is the formula for it. Okay. There is an actual formula that Jesslyn and Jovita, you will do it in the NEET class because that is there for you all. So right now I'm not telling here. We'll do it in the batch when we'll come to magnetics. Right now for your board exams, just remember the formula because you'll not get the questions just like this. The questions will be, I'll show you some questions. Yeah. Look like this. Wire is there, semicircle is there, like this. This is how you have the different shapes present. Now, another one is the semi-infinite. Finite is not there. Semi-infinite means one end is extending up to infinity. This end is fixed. And the point that you are calculating is lying on the finite end, not at the infinite end. It is lying at the finite end. This is important that your point is lying at the finite end. So formula is V is equal to mu naught I divided by 4 pi. So in both the cases, magnetic field is inversely proportional to A. And this is the point that the point is lying near one end means, and which end? One end means the finite end. Finite end means one is infinity. For semi-infinite, semi means half. Half is infinity, half is fixed, the other half is fixed. So your point is lying at this half which is fixed. And the kind of graph you will get will be a hyperbolic graph because your magnetic field is inversely proportional to the distance. Now tell me all of you, have you understood everything till here?
Yes, ma'am.
All right. Okay, Jesslyn, Saima, Jobita, is she there? Yeah, Jobita, clear to you? Please write it all.
Ma'am, can you scroll up?
Done? Should I scroll? Just let me know once written till here at least. All those who have done till here, just text me a done. Jasleen, your assignments I haven't received. You said you have submitted. Please check.
Done,
I
ma'am.
have not received a single. Done. Shaima, your assignment was very good. The last assignment on the electric power which you submitted, it was very good. Very well done and properly written. Others also give the homework so that we
Ma'am,
can
the
discuss.
one I uploaded today.
Yes, yes, that one, electric power. That was done very well. All the steps were written properly. Okay, class, if you've written till here, you can leave because the time is up. This part you can write it in the next class. Then we'll discuss the questions also.